Hello, I'm Dr. Ian McCullough of Johns Hopkins University. This is a short lecture on the use of the R programming language to work with continuous random variables. This is not meant to be a standalone lecture. This is meant to accompany another video lecture where we work out some of the principles and theory behind continuous random variables on the board. If you have not seen that lecture, then I would ask that you stop this video now, review those first, and then return to R to see how to actually work problems taking advantage of the software. So this is an R script, and I'm going to draw your attention to the scripting window that we have right here. And this is where I'm going to illustrate the commands, and then you will see results appear down here in the console. For this exercise, we'll not be using the global environment or any of the other features here in RStudio. So the first thing I'm going to ask you to do is enter the command to just clear the workspace. And so we just go up here to the little run command, and I can run that command, right? And then the workspace is cleared. We're now going to look at how we use R to calculate some problems dealing with the normal distribution. So if you refer to example 4B on page 202 of your text, the problem is basically telling you that x is a normally distributed random variable with a mean of 3 and a variance of 9. And the first question is find the probability that a randomly sampled variable will be between the values of 2 and 5. So we use the pnorm command here, and so pnorm we're going to enter in 5. And what this is going to do is this is using the distribution function. So this is going to tell us the probability that a randomly sampled variable is going to be less than or equal to 5. And the mean is then defined as 3, and the standard deviation is defined as 3 because the square root of the variance is 3. And then we're going to subtract what we don't need from this set, which is the distribution function for a random variable of 2 or less. Same mean and same standard deviation. And so that will give us the probability that a random variable falls between 2 and 5 given those parameters. So if we go here, we can calculate run, and then you can run that to make sure that you have the same result of 0.3780. And that will also match what you have in your textbook. You will note that the answer that I'm using is more precise than the tables. So if you look at the book, there are some tables in the back, and the tables are basically people back in the day have gone through and calculated the probabilities given a standard normal distribution, and then the book tries to have you convert any normal distribution to a standard normal so that you can look up those integrations in the back of a statistics textbook. Well, today that is as outdated as long division or cursive writing. We have computers now that can run that and be far more precise and far easier than trying to memorize this whole procedure of how you're going to look up values in the back of a textbook. So we will not be covering how to do that. We'll now look at a different problem. If we go to part B of the same problem, example problem, you're asked to find the probability that x is greater than 0. So now we're not looking at a less than value, we're looking at greater than. So this is where we're going to have to say the probability that something happened is 1, and then subtract out the pnorm, the distribution function, saying that the variable is less than 0. So we know something happened, that's the 1, and now we're going to subtract the probability that x is less than 0, and then there's the parameters for that normal distribution, and so when we run that, we end up with 0.84. Now, I'm going to tell you there's an alternate way of doing this because, R wants to make things a little easier for you. So instead of doing the 1 minus, if you want to instead flip it and just ask directly what's the probability of being greater than 0, then you can add this additional parameter here called lower.tail equals false. And so basically you're telling it, I don't want to look at the less than value, I want to look at the greater than value, right? So if we run that command, you will see that you have the same result. Okay, so we're now going to go and do something a little trickier. If we look at problem C, find the probability that the absolute value of x minus 3 is greater than 6. Well, we have to do some algebra. This is where the material covered in the lecture becomes important. This becomes an excellent exam problem because it requires you to not only know how to use R, but it also requires you to do some algebra and know something from the lecture as well. So if we work out the algebra of the absolute value of x minus 3 greater than 6, we're really asking what is the probability that x is greater than 9 or the probability that x is less than negative 3. So we need to add these two. So when we're adding probabilities, we can just do the probability that, and I'm using 9. Here's the parameterization of the normal distribution, and then I'm saying lower tail is false, meaning I'm looking for greater than 9, plus the probability that we have less than negative 3, same parameterizations. And so then when we run that, you'll find that you can match that up with the value in your book. Let's look at another problem. So problem example 4D in page 203 of your book says that human gestation is normally distributed with a mean of 270, a variance of 100. And they're talking about a court case where a defendant is doing a paternity suit, and he is saying, hey, he was out of the country from 290 days to 240 days before the birth of the child. So what is the probability that the defendant could be the father? And so now we will use the P norm of 290. Here is the mean, 270. Standard deviation is 10 because, again, it's the square root of the variance, is standard deviation. And we are saying the lower tail is false. So what is the probability that we could be greater than 290 plus the probability that he could be less than 240 days, right? So that is outside of that range of 240 to 290 is what we're looking at. And so then when we run the probability, it's a little over 2%. Okay. So this is basically demonstrating how we would use R to calculate probabilities using the normal distribution. We can also work on other problems dealing with different distributions, and we just have to replace the command in R with the correct distribution, and the parameters might change a little bit. So I'm going to give you an example of a couple of these. First one we're going to look at is the exponential distribution. So I'll draw your attention to example 5b on page 209, and they say that the length of a phone call is exponential with parameter 1 over 10. If somebody arrives immediately before you, what is the probability you must wait, A, more than 10 minutes? So now, instead of using P norm, we're going to use P exp, right? So this is the probability for an exponential. Again, this is the distribution function, so the CDF, and we're saying what is the probability that, normally you would say, what's the probability you're less than 10, but see I have the same lower tail parameter here, so I am using that to say what's the probability I'm greater than 10 minutes. The rate for the distribution, the parameter, is 1 over 10, and so when I run that, you can match that up with the answer in your book. The part B of that question is, what is the probability you are between 10 and 20 minutes? So now this is where we would use, what's the probability you're less than 20 minutes minus the probability you're less than 10 minutes, right? So that is how we would do the middle. And you end up with the probability of 0.2325. And again, you can match that up with your book. We'll now turn our attention to example 5D on page 211 to give you another example. So the number of miles a car can run before the battery wears is exponentially distributed with an average value of 10,000 miles. And if a person wants to take a 5,000-mile trip, what's the probability she can complete the trip? So for this problem, we have to recognize that the rate parameter in an exponential distribution is 1 over the mean, or the mean is 1 over the rate parameter, however you want to look at it. So I'm going to, instead of dealing with these really, really large numbers, I'm just going to do my problem in thousands of miles. So the rate parameter is 1 over 10,000 miles, right? So 1 over 10 is the rate parameter. So then the probability I'm going to look for is the probability that I am 5, and I'm using this lower tail. So what's the probability I'm going to be greater than 5,000 miles using this rate parameter? Okay, so that is the probability that the battery is not going to wear out before 5,000 miles. And when you look at that 0.606, you can match that up with the result in your book. Okay, so we're now going to look at the gamma distribution. So there isn't a really good example problem in your book, so I've made one up for you. So for the gamma distribution, let's say you're fishing and you expect to catch a fish once every half an hour. So we want to compute the probability that you'll have to wait between 2 to 5 hours before you catch 4 fish. Okay. So let's look at the parameters here. So 1 fish every half hour means that you expect to get 1 over half an hour, or 2 fish an hour, right? And so that becomes your beta parameter in the gamma distribution. It's how many fish do you expect to get in this hour, right? And so the question is asking the probability of catching 4 fish. So alpha, this is like your criteria that you want to see, is how many failures, or how many observations, or how many successes, however you want to call that, is going to now be alpha, and that alpha equals 4 fish. So if I want to ask the question, what is the probability that we are catching between 2 to 5 fish, or sorry, waiting 2 to 5 hours to catch the 4 fish, 2 to 5 hours, well then I have to calculate the P gamma. Notice the pattern here, right? So this is still a CDF, and we're looking at P gamma is the probability we're less than 5 hours, right, to catch 4 fish at this rate, minus the probability that we're going to be less than 2 hours to catch the 4 fish with that rate, okay? And so the result then is 0.2234, and you can check that on your own. There's not a book to reference for that, unfortunately. We can also use the scale parameter. So this is showing you a rate, right? So that's going to be kind of what we've been used to dealing with, right, for our formulas. But you can, for the gamma distribution, you can replace rate with scale, right? So you wouldn't use both of them, one or the other. But the scale parameter is just 1 over the rate. And so that is another way of executing the same problem. You can see the results are the same. So we're now going to move to our final distribution of this short video, which is the Weibull distribution. And so the Weibull distribution has some extra parameters and just a more robust distribution. So the example problem here is the failure times of a particular electrical component are Weibull distributed, and we have these parameters: beta equals 2, alpha equals 1,000 hours. Consider alpha to be like the mean time before failure. It's usually used for reliability problems. And so the question is, find the reliability of one of these components if mission time of 100 hours, and then the second part of the question is, and the hazard rate after the tube has operated successfully for 100 hours. So for the first part of the problem, what do you think the command is going to be? Just think about it for a minute. Well, if you answered P Weibull, you would be correct. So we're going to test P Weibull, that the probability that it's greater than 100 hours, because I'm using what, lower tail equals false, and then our beta parameter is 2, and our alpha parameter is 1,000. Now I know it's a little unusual in R that we're going to use beta first and then alpha, but I didn't write the code, I'm sorry. So beta is 2, alpha is 1,000 is the parameters of your distribution, and then when you run that, you get a high likelihood that that's going to run more than 100 hours. Now for hazard rate, we discussed hazard rate in the lecture, and if you actually put up the distribution and you work out the math, you will actually derive a hazard rate, and it will end up looking something like this, like negative CDF of 100 hours, 2,000, lower tail, and we're going to take the log true, and that will give us the hazard rate, which is going to tell us that there is about 0.01 parts per 1,000. Alrighty, we're going to cover one more thing that we have here, which is the generating random numbers. And I just think this is interesting. So if you use R norm, so before we used P norm, PX, P gamma, well now what we're going to use is we're going to use the R's, right? So if we use R, this is generating a random normal number. And so if I just run that real quick, you'll see that this generates 10, that's the parameter there, 10 random normal variables with a mean of 0 and a standard deviation of 1. We can do the same thing for exponential, right? And so you can generate 10 random exponential, or gamma, or of course Weibull, right? So you can see that. We can also generate more numbers and then estimate those distributions. So if you look here, I can generate, so x norm is a variable, I can generate 100 random normal variables with a mean of 5 and a standard deviation of 3. Okay, and now I can estimate from that vector of random numbers, well, what is the mean likely to be or for this generated numbers, right? And you'll see that that is 0.516. If I were to run that command again and estimate the mean, right, you'll see that it's a little bit different. And that'll be different every time you do it, but it'll be approximately a mean of 5. And if we run the standard deviation, again, it's approximately 3. Okay, we can do the same thing with a exponential. So if I create another random variable for exponential, right, and then I estimate the mean, what should the mean be? Well, the mean should be 1 over 5, because that's what we know about the exponential random variable. So let's see if that value, 0.19, is 1 over the mean. So you'll see that that is approximately 5 for that lambda, or that rate parameter. And then the variance, right, 1 over the variance should be roughly 25, right, because it should be lambda squared. And so if we run that, we're a little bit further off, but if we were to run this again as an example, and let me see what our parameters are, right, and so you can see that, again, these kind of are rough approximations to estimate those parameters. This has been a short lecture on continuous random variables in the R programming language. I'm Dr. Ian McCullough from Johns Hopkins University. Thank you for joining.